Hello and welcome back to a new session. In this video, I would like to discuss transformers, what these devices do and how they work. And I would like to start this session with a story. More than a century ago, a technical genius and a financial genius fought a series of battles about what kind of power distribution system America would use. Edison, yes, that Edison, was pitching the DC or direct current transmission system, while his rival, Nikola Tesla, who is the gentleman you are seeing right now, was pitching the AC or alternating current distribution system. Based on winning this battle, they would be able to control hundreds of millions of dollars in the coming years in the form of generous grants by the US government. Tesla would go on to lose this battle and ultimately win the war. Let us see why. And let us see what role transformers played in his victory. So what is a transformer exactly? In the simplest, most basic terms, a transformer is a device which is used for changing alternating voltage. I'm sure you have seen transformers at some time in your life. For example, this one is at an electrical substation, which is used for feeding power to large cities or factories. How does this device work? Well, in the simplest terms, it does so through the principle of mutual induction. All transformers, small or big, have the same basic construction. There are at least two sets of coils which are wound on a laminated soft iron core. And it does not matter how big or small the transformer is. For example, if you observe this device, which is small enough to easily fit inside your hand and belongs on a circuit board, and compare it to the previous device that you saw, you will notice that both of them have the same basic construction. They have a laminated iron core around which there are at least two coils of copper wire. The primary coil, which is often called the input coil, is said to have NP number of turns, while the secondary coil, also called the output coil, has NS number of turns. So here is a schematic diagram for a transformer. You can clearly see that in this case, there are two coils which are wound separately, the primary coil and the secondary coil, and both of them are wound around a soft iron core. The two coils can be wound up either on top of each other, or both the coils can be on separate limbs of the core. To see this, let's look at this schematic. In this schematic, we can observe that both the primary and secondary coils are wound around a common core. However, it is very important to understand that both of these coils are insulated both from each other and from the core. In other words, there is no electrical contact between the primary and secondary coils or between them and the core. They are completely electrically insulated. On the other hand, this is a more conventional construction that you often see in books. In this case, we have two separate coils wound on two separate limbs of the transformer. Whichever scheme is used depends on the specific requirements of the project that the transformer is used on. Since the two coils have high mutual inductance, when an alternating current is applied to the primary coil, it produces an alternating magnetic flux. Now, what does this mean? Let's look at a simplified diagram. So in this diagram, you can observe that there is a primary coil and a secondary coil, and they are wound around two separate iron cores. These iron cores are not in physical contact. And yet this device will work. What will happen is that the AC generator, which is sending an AC current through the first coil, is generating a flux which is changing with time. This flux is traveling through the air and is also engaging with the soft iron core of the second coil. And as a result, it will induce an EMF in the second coil. The purpose of using a solid iron core, which is magnetically in link with both coils, is to improve the flux density inside the coil, which in turn increases the efficiency of the EMF being generated in the secondary coil. On the right, you will see the symbol of the transformer. You can clearly observe that we have schematically represented the primary coil, followed by the core, followed by the secondary coil. The lamination of the core is also clearly visible. In an ideal transformer, the primary has negligible resistance and all the flux generated in the core links both the primary and secondary windings. So in other words, there is no leakage of flux outside the core of the device. There is no wasted flux. And also there is no resistance in either the primary or the secondary winding. So there is no power loss caused by I square R losses. Considering that phi is the total flux in each turn at time t, when voltage Vp is applied to the primary coil, the induced EMF or the voltage Es in the secondary coil with Ns turns can be calculated using this equation. So the equation says that Es is equal to negative Ns d phi by dt, where d phi by dt is the rate of change of flux, where the negative sign is in accordance with Lenz's law. The above application also produces a back EMF in the primary. This can be calculated as Ep is equal to negative Np d phi by dt, where Np is the number of turns in the primary, d phi by dt is again the rate of change of magnetic flux through the core, and the negative sign is in accordance with Lenz's law. It is also noticed that in such cases, Ep is equal to Vp and Es is equal to Vs. That means that the increase or decrease in the primary and secondary voltages with respect to each other are in the same ratio as the turns in the primary and secondary windings. It can thus be said that Vs upon Vp is equal to Ns upon Np, or the ratios of the primary and secondary windings are exactly equal to the ratio of the turns of the primary and secondary coils. When the secondary coil has a greater number of turns than the primary, the voltage is stepped up. Such transformers are known as step-up transformers. So in such cases, Ns will be greater than Np, and Vs, that is the voltage induced in the secondary winding, will be greater than Vp, that is the voltage in the primary winding. However, if the secondary coil has less turns than the primary, we have a step-down transformer, or Vs is less than Vp. Transformers transmit and distribute electrical energy over long distances. So coming back to the original question, why did Tesla win the war ultimately? Well, the reason is that there is no simple or easy way of stepping up a DC voltage. A DC voltage can only be stepped up using extremely expensive devices which will fail over short periods of time. On the other hand, the transformer is a relatively simple, relatively inexpensive and very effective device for stepping up or stepping down AC voltages very conveniently. The reason this is important is that in long distance transmission, the biggest problem is the loss of energy caused by I square R losses. The lower the current we use, the less the losses. So it is advantageous for a power company or a power distribution system to transmit power at the maximum voltage and the minimum current possible, which is only economically possible with AC voltages. The current is transmitted to an area substation at high voltage, and then for further distribution to other substations which step down the voltage to a level of 240 volts, and that is what is applied to our homes.
Manorama Horizon. Learning made simple.